Hello, my name is Aileen Perez and my partner Jorge Figueras, and today we will be presenting our Phase A of Capstone1 Functional Finger Prosthetic Design. In the outline we have technology assessment at the system level, trade studies, project and mission architecture and interfaces, and the budget. For each subsystem, we will discuss the owner, requirements, risk assessments, and our project plan. For technology assessment at the system level, we have three references. The first is a paper called Optimization of Prosthetic Hands, utilizing modularity to improve grip force, grasp, and versatility. The second one is 3D printed prosthetic hand, and the last one is the Smart Hand Transradial Prosthesis. For trade studies, we have three alternatives. The first one is the Model K1, weighs 99 grams, has wrist flexion, costs $50, 5 degrees of freedom, and a force of 3.2 kilograms per force. The second model is the Phoenix Hand V2, weighs 110 grams, wrist flexion, $60, 5 degrees of freedom, and a force of 4.5 kilograms per force. And the last model we have is the Talon Hand 3.0, weighs 83.9 grams, wrist flexion, costs less than $100, 5 degrees of freedom, and a force of 4.5 kilograms per force. These are some of the descriptions of the models previously stated. The first model, Model K1, is the most commonly used 3D printed hand. Uses string tensioning mechanism to allow for grip actuation upon activation and elastic spring back during relaxation, and has a decent level of realism. The second model, the Phoenix Hand V2, has a more concave fingers and palm for holding objects. Uses tensioning pegs, moderately realistic, the fingers are not exposed and allow for a pinch grip. The last model, the Talon Hand 3.0, is the most durable enable hand design and has the greatest grip strength. Is the most challenging and time-consuming to assemble and mounts onto a leather shoe and cuff to make it wearable.
Here we have our trade studies, rating weighting method, we have problem statement, choose a hand prosthesis that best meets the requirement of the client. Of our three options, we have a winner that is Talon Hand 3.0. We have the problem statement. Here is a diagram of our contributions. We are going to improve the product that we choose by implementing a motor and sensors to increase the force to 8 kg force or better, so that it meets the client's requirements, and modifying specifically for partial finger amputations, and it will continue to work with wrist flexion, but thanks to the motor each finger will move independently without to bend the wrist. That is what I call it hybrid. Here we have our project mission architecture. We have Talon Hand Prosthesis automated system with subsystem 1 electric motorized system and subsystem 2 mechanical design and activation. Here we have N2 diagram. We have the patient. We have to install the straps and install the electrode sensor. We have the Talon hand, and for the Talon hand we have the sensors to have to send a signal to the motor to start and a signal to the motor to stop. We have the motors who have cables to the fingers to move. And with the fingers, we have the force grip to the tail on hand to have to hold 5-pound objects. Here we have our budget for an investment of 5K prosthesis. It requires a budget of 1 million. If you sell 5K prosthesis at 300 each one, we have a gain of 1 million and a half, having a net income of 500K. Budget for 5K prosthesis is 700 for electrical motorized system and 300K for mechanical design and activation. Here I have my MOPs of electrical motorized control system. First, sensor electrode must fit on 5 to 6 centimeters diameter of the skin. Sensor electrode should captivate 100 millivolts action potential. Circuit should be reliable to send 5-volt DC to the motor. Microcontroller must work with 0 to 5 volts input and output. Torque of the servomotor should be greater than 100 newtons. Should have long use battery, at least 8 hours of daily use. Must have good wire connection to send 100 millivolts efficient at the circuit. Here we have the risk assessment. The risks are wires or disorder disconnection. Batteries discharge quickly. Motor is not receiving enough current. Motor could be stuck. Sensor do not receive enough signal. Sensor do not attach correct to the skin surface, and circuit is receiving error signals. Here we have the risk assessment matrix, where red as a high risk, yellow as a medium risk, and green as a low risk. Here we have our mitigation strategies. For risk A, wires must be quick connection and good soldering. For risk B, use lithium rechargeable batteries, 500 charge cycles. Risk C, check battery if necessary, change adjustable DC power converters. Risk D, motor will be one of these servo motors. Risk E, sensor will be malware muscle sensor. Risk F, sensor can have gel electrode and AGCL for best receiving signals. And risk G, build a cover for circuit for signal interferences. Here we have our complete project plan for this subsystem. We have the dates of presentation for phase B as October 20 and phase C1 November 1.
For this subsystem of mechanical design and activation, the MOPs will be the following: high durability of the materials, must resist temperatures of at least 120 Fahrenheit, durability of the cables between the fingers, must have a grip force enough for lifting objects of 5 pounds, correctly anatomic design. The device has both a fist and a 3-finger shock grip, and the device caters to partial hand amputation patients. This is the risk assessment for this subsystem. To the left, we have the risk, and to the right, the matrix that will let us know if the risk is high, medium, or low. We have the first risk, locking mechanism failure, that is a high risk, cord release, a medium risk, elastic release, a low risk, tension pin failure, medium risk, finger failure, medium risk, strap failure, low risk, and deficiency in the grip of objects, that is a medium risk. For this subsystem, the mitigation strategies are the following. Choose materials with greater durability. See convenient cable materials. Choose material with high elasticity and high melting point to avoid deformations. Reduce friction between prostheses and cables. The function of each joint must be well made for every finger, making the right anthropometric measurements so straps will not fail, and research and analysis of the separation of angles of the thumb and each finger. Here is the complete project plan of the subsystem. The Phase B will be presented on October 20, and the Phase C1 will be presented on November 1st.